All right, so I've come up with an upgrade for the SAIC RTR-4 integrated imager to replace the existing OEM camera with a newer, more modern industrial Ethernet camera to provide higher resolution and enhanced capabilities. So here is the original SAIC RTR-4 system as in its factory default configuration. It has its OEM camera looking off a mirror at the X-ray intensifier screen, and it's controlled by an image grabber board, which then interfaces by Ethernet with the computer and is run by the custom SAIC software. This board is connected through a power and relay board through two pin headers. One of them, this header here, has the X-ray trigger output. So there's a 6-pin header, and the pin furthest to pin 1 is ground, and pin 2 is trigger. It's pull low, so if you short that to ground, it closes the relay, which connects the output port to fire the X-ray generator. And here is an illustration of all the pinouts on this board. So this, looking down from the top at the board assembly here, so that's like so. This right here is power and Ethernet. So pins 1 through 4 are Ethernet pins. Pin 1 on the header is Ethernet pin 3 on Ethernet connector. That is the orange dashed wire. Pin 2 is Ethernet pin 6, orange solid. Pin 3 is Ethernet 1, green dashed. Pin 4 is Ethernet 2, green solid. Pin 5 is then ground. 6 is not connected. Pin 7 is positive 12-volt supply to the frame grabber board, and then pins 8 through 10 are non-connected. On the X-ray trigger connector, pin 1 is ground. Pin 2 is X-ray trigger pull low. Pin 3 is wired up on the connector, but I have not been able to determine what, if any, function it's assigned to. And then pins 4 through 6 are not connected. The camera is connected to this pin header. There are 4 pin headers. This also works on the SAIC RTR-4L version, which has a 4 times larger screen with 4 cameras looking at a image intensifier screen, which is 4 times larger. Okay, so the camera by default on the RTR-4 is a custom OEM camera that was designed specifically for this system. It, by default, looks through a 6.3 millimeter f.8 lens. It's not a C-mount. It seems to have some custom or unusual thread, but I'll note that it's an f.8 lens, which is a very fast lens, so it has high light gathering capability. And it looks off of a mirror on this angled piece of aluminum and then reflects down to see the image intensifier screen, which is exposed to the X-rays. The intensifier screen is a green phosphor. It glows green, and then that is recorded by the camera. Unfortunately, this camera is rather low resolution. This is 772 by 582 pixels, so it's 0.4 megapixel. This will be This is now upgraded to 2 different types of cameras. The Basler ACA 3800-10 GM, which is a monochrome camera. This actually, this is the ACA 10. So this is 3840 by 2748 pixels, which is 10.5 megapixels. It has a 1/2.3 inch CMOS sensor, which is 7.9 millimeters effective diagonal, and it uses a rolling shutter. The pixels are 1.67 micron squared, and they have around 40% quantum efficiency in the green spectrum. This would be equipped with a Basler C125-0618-5M lens, which is 6 millimeter at f1.8. So the light gathering capability isn't as good, but it's still a pretty good match to the camera. This or other type of camera would be mounted on a custom aluminum plate, which aligns it with the center of the field of view. The other camera, which is used in these test upgrades, is the Basler ACA 1920-40GM. This is 1936 by 1216 pixels. This has a global shutter. It's also a CMOS camera at 2.3 megapixels. This is a 1/1.2 or roughly 13.3 millimeter diagonal CMOS detector. This is 5.86 micron square pixels, which gives it approximately a 70% quantum efficiency in the green spectrum, and it's equipped with a Kowa LM8HC 8 millimeter f1.4 lens, so slightly better light gathering ability, but the greatest increases in sensitivity will be due to the larger quantum efficiency due to the larger pixel size. It's also worth noting that on the ACA 3800 CMOS camera, it has a 34 decibel signal noise ratio, whereas the ACA 1920 has a 45 decibel signal noise ratio, so it's also going to be lower noise at the expense of lower resolution. So how this upgrade works is these are gigabit Ethernet cameras, so they'll need an Ethernet port. To accomplish that, a hole has to be drilled in the side of the case of the RTR-4. This is just an Ethernet bulkhead feed through, and this will cable up to an Ethernet extension cable for the camera. So this is the only modification that you have to make physically in the case. And this is, you'd be drilling a 13/16 hole, roughly slightly larger than a 20 millimeter diameter. Then you basically scoop out all the OEM components. You pull the camera and the frame grabber board out, and those just disconnect via pulling the two snap-on headers. Those are of the Molex SL series connectors. There's a 10-pin and a 6-pin. The 10-pin interfaces with DigiKey WM2537-ND. That's the 6-pin. And the 10-pin interfaces with DigiKey WM2541-ND. So those are the matching connectors, and then those use 20-24 gauge crimp pins, DigiKey part number WM2515-ND. So basically what that looks like is you take the Ethernet camera and you build a basically just a pin header to adapt it to the existing circuitry. That just plugs in the back. And then you have the 6-pin for the X-ray trigger. The X-ray trigger is connected to the pull low output pin on the Basler camera, and that is connected either to the flash window, and that is set to either pull low on the flash window if you have a rolling shutter, or the exposure active if you have a global shutter. So the difference between rolling shutter and global shutter on a CMOS sensor is global shutter, you turn on all the rows, all the lines to expose simultaneously, whereas with rolling shutter, in this case, this has a global reset release function, so you can start all lines integrating simultaneously and then just read off the first line, second line, third line, fourth line. The issue with that is the bottom lines have a higher exposure than the top lines because they've been integrating longer. However, since the X-ray pulse is only about 50 nanoseconds long, but then there's phosphor afterglow, usually you'll catch the whole pulse, or if you're integrating over multiple pulses, this isn't typically that much of an issue on this system. So once you have all of the electronics scooped out, basically it looks like this. The camera board sits on top of, these were machined by Front Panel Express. They're 4 millimeters thick. You'll want to have them sit on top of a 7/16 inch long standoff, which brings the total height to the bottom of the camera above the places where the original OEM camera screwed in, about 15 millimeters. So this camera module then drops in, and this just screws down with 632 screws. And the camera center line is about 1.25 inches this way of the center of this hole. So that will bring the camera lens centered into the same place as the location of the OEM lens. And once you have that installed, the pin headers then just connect with the existing Molex connectors like so. And that connects the camera outputs, the camera output of the exposure active to the relay control for X-ray generator fire, and the power connectors to the camera. The camera can take 12 to 24 volts, and it connects it to the 12 volts coming out of the power module. So this reuses the existing battery module and power conditioning, so you get that nice 12 volts, and this will power the camera. Now, the existing cable that came with these RTR-4 units used a custom LEMO cable. That's this green pin there. However, the LEMO connector only connects pins 1, 2, 3, and 6 of the Ethernet cable, so it'll only work on 10 megabit Ethernet, not gigabit Ethernet. And these are gigabit Ethernet cameras. They'll work on 10 megabit Ethernet, but the frame rate will be drastically reduced. So that's why on this modification, I'm actually installing this bulkhead Ethernet connector to get that higher communication rate with the camera. It's also a lot more convenient because if you are modifying one of these units from scratch, you don't have to go ahead and build this whole custom cable assembly. So with some more decoding on this, I've also decoded the functionality of the connector in the back. So the key is there. So looking at the connector key, so the red is where the key is on this. Basically, it has 2 5-volt lines, a number of ground pins. It then has an X-ray trigger signal. This is X-ray on. This is pull high to 5 volts. X-ray off is pull low to 0 volts. And then it has the 4 Ethernet pin connectors here. This pin is Ethernet 2. This is pin 2 on the Ethernet jack. This is pin 1, pin 6, and pin 3. So this entire unit would accommodate an RF module that wirelessly communicates with the host computer, and also wirelessly communicates with the wireless module on the X-ray generator to trigger that remotely, so that would convert this whole unit into a wireless system rather than a wired system. So it's more convenient, and you don't have to spool out cables. So that is all the pin decoding on all of these boards. And that is how this new upgraded system works. So once you have the hardware upgraded, it will no longer use the existing SAIC software. It'll use the Basler Pylon software, and you have to do some configuration of the cameras and that to get them to function correctly with the X-ray generators, and I will go into that on a future video.